All right, welcome everybody to today's CDAC webinar. Today we're very pleased to have Stefano Racioppi from uh, Cambridge. Stefano is a theorist who's worked on a variety of problems, beginning with molecules, molecular systems, problems in structure and bonding and reactivity, and more recently in the solid state, including structure, bonding, and interesting properties that emerge under pressure. And he's looked at a wide range of phenomena, including novel phases, including electrides and novel compositions of perovskites. Stefano got his PhD in Milano. He was a researcher at the postdoc level in Sweden, and then was for a number of years at Buffalo, where he worked with Eva Zurich and contributed to quite a few papers in CDAC. And this continues, including one that was just submitted last week. And a few months ago, he moved to Cambridge, where he's working with Chris Picard on similar problems. Stefano gave a talk back in, I guess it was March of 2023. And so this is round two for Stefano. And we're really pleased to hear about your new work and this really important area of using these structure search methods combined with experiment to solve crystal structures and look at properties in high pressure phases. So over to you, Stefano.
Thank you so much for the kind introduction. And yes, I will try to kind of show some recent developments in the multi-objective crystal structure predictions that, and particularly I will talk about two recent papers that I did with Eva. One is about the use of experimental powder X-ray diffraction data to assist the crystal structure predictions. And the most recent one is about the use of topology of the electron density to predict new electrides. But first, let me quickly introduce Excelopt. That is the crystal structure prediction code that I use for this analysis and the crystal structure predictions in general. So, crystal structure prediction techniques aim to explore the potential energy surface of a given stoichiometry at certain conditions. And it does so by generating and locating the structure that correspond to the local minima and the global minimum of the potential energy surface. There exist really many codes that can do this job using very different methodologies. Here report AIRS, Calypso, and also Excelopt. That is the one that I use, and in fact there is no unique recipe to solve this problem of localizations on minima. So Excelopt is a structure prediction code developed by in the group of Eva Zurich. And it is an evolutionary algorithm that act the typical operations of breeding and mutations to a unit cell to generate new structures, and in this way, through these offspring that are mutated and breeded, Excelopt can explore the potential energy surface of a given composition. In evolutionary algorithm, there is this fitness parameter that is assigned to each offspring that is based upon their energy or enthalpy, and the probability of using one of these new child of new structure as a parent for the new for the next generation. This probability is indeed based on this fitness parameter. Traditionally, Excelopt and also all the other crystal structure prediction methods aim to minimize the enthalpy to find the thermodynamic most stable structure. However, we can imagine to use also other properties or combination of properties to guide our crystal structure predictions. Therefore, we can design and customize new fitness parameters that allow to perform multi-objectives. So this fitness parameter now is depending on more than one objective, not only the energy. This is what Samad has recently developed, and this strategy was revealed to be particularly effective to search metastable phases. And this multi-objective strategy is also at the core of the method that I will present. So yeah, let's see how we can use then experimental Podex diffraction to guide the structure predictions. First, we know that to obtain structural information from a sample, X-ray diffraction is usually the best way to go, even if it's not the only one. If the sample that we have is a nice single crystal, then the structure solution can be relatively easy. This is not the same if the sample is a powder, since we are basically merging all the peaks of our diffraction along just one dimension. And this causes some loss of information and makes the structure solution quite challenging. Therefore, oftentimes we are asked from experimental collaborators to perform a crystal structure prediction to help the characterization of new compounds for which the Podex diffraction was collected, but that was still particularly challenging to solve due to this problem. So theoretical calculations in this case should support experimentalists for such identifications. The standard procedure was to run a crystal structure prediction to check the Podex diffractions of the most stable phases, and making this comparison between the theoretical and the experimental Podex diffraction. And if we were lucky, we would associate a theoretical structure to the experimental data. This method, however, was very inefficient, and it was easy to miss good structure, especially if they were not the thermodynamically most stable at a given level of theory. Moreover, and most importantly, we know that the structure we calculate cannot perfectly match with the experimental data, so with experimental Podex diffraction, due to the various approximation that we use, not only the DFT functionals, but the fact that we are doing a calculation at 0 Kelvin and so on. And this is particularly true when we try to compare our calculation with data collected maybe at a high temperature or high pressure, since even small differences in the unit cell can have quite a big impact in the Podex diffraction pattern, making this theory to experiment comparison not always so straightforward. Therefore, I tried to improve this procedure, and in particular, I wanted to achieve a couple of goals. The first one was to implement an automated quantification of the similarity between the calculated and the reference Podex diffraction that was supposed to be the experimental one. Then I wanted to have a method that could account for all the deviation from an ideal crystal structure. So incorporating the formations that could emulate or simulate the finite temperature or anisotropic compression that would happen in a real structure. But I wanted also to do that on the fly, so without the need to perform expensive quantum mechanical or quantum molecular dynamics simulations. The first problem can be solved quite easily by calculating a similarity index, for example, based on the cost correlation functions, like in this case. Since what we calculate in the end is actually the degree of a dissimilarity between two diffractograms, the value 0 means that the two Podex diffraction or two diffractograms are nearly identical, while one gives the highest level of dissimilarity. Solving the second point instead was very tricky. Fortunately, after a visit at the University of Oviedo, I started a collaboration with Alberto Otero de la Roza who was working on a similar problem and who developed a method called the variable cell Gaussian powder-based similarity index. This method can take a calculated structure from, for example, a DFT optimization and compare the product diffraction of this optimized structure with a reference that is, in this case, the experimental data. However, it further performs a series of anisotropic deformations of the unit cell, of the calculated unit cell, while checking the similarity index with the reference product diffraction. So the cell parameters that are now deformed are basically optimized until the best configuration of the cell parameter is found, and that is the one that best matches the reference product diffraction. In this way, we can basically generate a unit cell that match experimental data without actually accounting for all the phenomena that would actually give it these deformations. So this routine is now implemented in Axtalopt, and the workflow looks basically like this. Once we generate the new structures and we optimize them with FT, the calculation of similarity index happens at this stage. And the product diffraction data that you can provide or that one can use is basically just a list of 2 theta angles values and the relative intensity. And this can be just a list, so there's no need for the indexing. Moreover, the list can also not be continuous. So what I mean is that this list can be also just a short list of the main peaks that one wants to consider from the diffractogram and not the entire pattern. Then a fitness parameter is calculated based on the multi-objective formulation that I showed before, done by Samad, by including the similarity index from this module. In this way, the crystal structure prediction will tend to generate the structure that better fit with experimental data, because now we're promoting those structures that have the structure parameter, but also those atomic disposition that fit with the particle diffraction, even if maybe they're not the most stable. Moreover, I want to add that the Poderix diffraction routine does not add any computational cost to the crystal structure search. In fact, this calculation takes only a few seconds on a laptop computer. But now, some results. So the first test that I decided to run was on the metastable phase of titanium dioxide that is called Brookite. So Brookite is not the least stable among the known polymorph of titanium dioxide, at least at ambient conditions, and according to DFT or PB-DFT, but it is the least symmetric. And sometimes it is problematic to find with the classic crystal structure predictions. Here you can see two classic searches, so single objectives that are based only on the enthalpy, where over 2 searches done on 1,000 structures each, Brookite was not found, while more symmetric structures like anatase and rutile were always identified, even if rutile in this case is calculated to be less stable. On the other hand, the new Poderix diffraction system method seems really to outperform, since it can identify Brookite in less than half of the structures, actually just in a few hundred structures. In this case, the reference that I used was the experimental data collected at the room temperature that I could find from the CCDC database. So the choice of the weight here that you see, that is this coefficient, that tells how much of an importance we want to give to either the similarity index or the energy, seems to be quite important. Because if this weight is too low, so meaning that we are giving too much importance or more importance to the energy, the advantage given by the similarity index doesn't seem to kick in, while if the weight is more or less 0.6 or 0.9, and the weight goes from 0 to 1, so that the search is almost completely driven by the similarity index, then we really see that we can find the brookite quite easily. Yes. Here, instead, you can see the structures of the three polymorphs and the relative Podix diffraction pattern together with the similarity index calculated after the refinement, so after the deformations and check of the similarity index. Well, below here I reported the similarity index calculated with the cell before the refinement. And you can see that the brookite is still the best match compared to anatase and rutile among these cases, but also that the similarity index is not really close to zero, since the DFT unicell does not really match with experimental data. Instead, after this automated cell variation, we can see that the output structures that now changes and start to be optimized over the experimental data is very close and very similar to the final product. So we can really say that the brookite is our match in this type of search. The second example I want to show is based on a ramp compression experiment. Here I'm showing the high pressure phase of sodium, called the sodium HP4. This phase is particularly interesting because it becomes transparent at more or less 200 gigapascal. And studying this type of exotic system is of great interest to understand the behavior of simple elements at non-ambient conditions. And that was what motivated our collaborators at the University of Rochester to study the behavior of this element in a ramp compression. And together with sodium HP4, this study identified an additional phase here at 315 gigapascal that was indexed as a R3 bar M, for which I reported the experimental data here. However, the nature of this phase appeared to be a little bit controversial from the theoretical point of view, since it was predicted to be dynamically unstable. So I said, okay, let's see if my method can find something else from this data. With a classic crystal structure predictions with FT optimization, one would find that sodium HP4 is the most stable structure at this pressure condition. But again, this structure will not fit or will not reproduce the experimental data, the diffraction data. The surprise was that, at least for me, was a surprise that when I used my method, the best match was again sodium HP4. However, something was obviously different. So the structure that appeared to give the best similarity index was a sodium HP4, which seems to be extra-squeezed along the C axis, as if the compression was not completely isotropic. This caused the C/R ratio to lower and also the density to increase. However, this structure generated with a powder X diffraction match give a diffraction that is really spot on with experimental one, is including this tablet here that I didn't even notice in the first glance. Now it's very hard to claim that this is exactly the structure that was observed experimentally. But I think that it is very interesting that without any information about a powder X diffraction pattern, a distorted sodium HP4, which is the thermodynamically most stable structure, was still found as the best candidate at these pressure and temperature conditions. And nonetheless, I want to highlight with that with this method, this method finally enables the exploration of distorted structures. especially at the extreme condition, which would otherwise be precluded with the standard DFT or molecular dynamic simulations. Okay. The final example here is a very tricky case of study, and this compound is called vaterite. So vaterite is a metastable phase of calcium carbonate, which is found in nature, whose structure has been a case of debate for basically a century. In fact, many structures have been proposed during the years, both from experiments and theory. Nonetheless, if the structure was solved, remained actually an open debate. Only very recently, first in 2013 and then in 2023, it was recognized that the experimental particle diffraction data could not be described by one structure only, or better. It seems clear that vaterite was in reality a polytypic structure, so a structure that basically contains crystalline domain which are not periodically consistent along one direction. Particularly one of the stacking direction. Moreover, this work showed that the two different monoclinic space groups could actually form this polytypic structure and explain the experimental observation, which were more or less favored thermodynamically depending on the temperature conditions. So, the success solution of vaterite has required the combination of so many different analytical methods. And this is a case that, despite the simplicity of the composition, I mean, it's just a calcium carbonate, this system could not be unambiguously solved only with the product diffraction, and surely not with the crystal structure prediction, since it is not able to capture different symmetry stacking and the features like a polytypic network, unless one would use a very extended supercell. Therefore, the question was, what can the method that I'm showing do to help the solution of these tricky systems? And in particular, if this method can support experimentalists to deal with these cases. So I found two data sets that I could use for microstructure predictions. One was an experiment done by DuPont in 1997 and another one by Lebel in 2021. Using Lebel dataset, I could find a AM2 structure that seems to be the best fit. So here I have the similarity index and here the enthalpy. Which was not surprising because this was also the structure that was proposed by Lebel, and this dataset is only was constituted by the indexed peaks. However, with the search I could find also other structures, many of those that were previously proposed by this one by Meyer or the one by De Michaelis, but there was also this quite stable PCA21 structure that was never reported previously. This phase was the only one in the pool of structure that could explain also this peak here that you can see at the 30 degree, which has always been attributed to calcite impurities, yet that was observed in every single particle diffraction pattern of vaterite that I could find. However, it also calculated this other peak here at 35, which is not really visible in the experimental data. Not sure if considered for preferred orientation could help, but therefore probably this PCA21 will not be the best candidate in this case. But you can see that we could generate many structures and also very stable. With a database by DuPont, I obtained a similar result, but of course not identical. So most of the phases here were found together with the new ones. But most importantly, I could find the C2 and C2 over C phases that are actually composing the polytypic model that I was showing before. And so this also shows the importance of the experimental, of the quality of the experimental data to run theoretical models. The take-home message in this case is that even if precise structure prediction cannot directly solve this kind of difficult problem, with our method we could generate almost on the fly 100 of years of structures and more, sorting them by energy and similarity index with the powder diffraction, which I believe could become an important complementary support for experimentalists when they undertake very challenging crystallographic problems. And in fact, we have already successfully used this method in multiple occasions, including this recent work done in collaboration with the Hamlis Group and led by Hassam, that you can now find in archive, in which the powder diffraction assisted search was crucial to identify a series of stable and metastable lead oxide phases formed upon the composition of lead titanate. Okay, so this is the second part. I do not know if we want to stop to do some Q&A of the first part, otherwise I can continue and conclude.
Are there any questions? Okay, why don't we proceed?
Yeah, I will just continue. Okay, so now let's see how topology of the electron density can help to predict electrolytes. So quickly, electrolytes in solutions or molecular electrolytes are known since basically the late 1800s, since scientists noticed that throwing a piece of sodium or lithium in a liquid ammonia, the solution turned blue or gold, depending on the concentration. The classic interpretation that was given was that due to the low ionization energy of the metal, the valence electron escaped, and the atoms from the atoms and were solvated basically by the molecule of ammonia. And here indeed was coined the term solvated electrons. But then, thanks to the great improvement of computational methods in quantum chemistry and also of the use of molecular orbital theory, it was possible to give a more quantum mechanically solid interpretation, seeing that the electrons are not really escaping but more transferred to the unoccupied orbitals of the solvent, so of ammonia, and these basically are forming clusters of these multi-center shared electrons, so that is delocalized between these molecules. But molecular and crystalline electrolytes can also form through generation of other multi-center bonds, like in this case of this magnesium 4 cluster that was observed experimentally, but also in the case of the activated mayenite. The good news is that basically all of these systems that we classify as electrolyte have in common a very specific feature of the electron density that is called non-nuclear attractor, or NNA. A non-nuclear attractor is a maximum of the electron density that, however, does not correspond to an atomic position. In fact, atoms are basically nuclear attractors that attract the electron density and they correspond to a maximum of the electron density when we try to map this quantity. And therefore, the presence of a maximum without a nucleus is quite uncommon, as you can imagine. Since non-nuclear attractors are then characteristic of the electron state, we can imagine to use them in our crystal structure prediction to improve the search of this type of materials. Therefore, what I did was to use the amount of the electron density that one would find at a non-nuclear attractor, which is basically a quantification of the concentration or the amount of electron density, so the level of electrolyteness of a system, as an objective in our crystal structure prediction. So the electron density I at the non-nuclear attractor now is maximized. So we want systems that have a lot of electron density in these non-nuclear attractors, where the entropy is minimized in this case, as previously. So we want stable structures. If no nuclear attractor was found, basically this objective was set to 0, so it was not an electroide. To test this method, I needed to find an interesting test case. And looking around, I was searching for a relatively simple system in terms of composition, so not too many elements, but maybe at least more than one. And that was confirmed experimentally. And that hopefully could show also electroid state, so since we wanted to search for the electroid. My attention then was caught by this system, that is calcium 5 lead 3. This is a quite a peculiar phase because it is synthesizable and it is synthesized at a high temperature, I think around 1300 Kelvin, despite the fact that calculation predicts that is very metastable. It is, I think, over 130 millielectron volt per atoms above the decomposition of calcium 2 lead and calcium lead. Yet this phase exists, and so I thought that was a very interesting case of study. However, this phase at ambient pressure is not an electroide. The good thing is that, the reason why I chose then this system as a test of case was motivated by this work done by Hosono and his group that predicted that squeezing this phase only up to 20 GPa, it would have undergone electrolytic state transition. So that seems very interesting, and I checked, and therefore I could check if my method could identify this phase and also accelerate the identification of these and similar phases. Our research, on one hand, this phase was found at 20 GPa, which is the one that here I report as the P63 over MCM. Here you have the relative entropy compared to this phase that is the 0, and also the amount of electron density at the maximum, so at the non-nuclear attractor. But on the other hand, it was found out that this was neither the most stable nor the most electrolytic phase at 20 GPa. So in this case, all this block or area where you see that there are phases with a value that is non-zero for the non-nuclear attractor, all of these are potential electrodes. Well, here this line at 0, those are all phases that are not electrodes because a non-nuclear attractor was not found. Now my search was found another phase that is this for P4 over MMM, that is up here. And that would be both the most stable and also quite a real electrolyte. So here this pink blob highlights the charge localization. Here you can compare other descriptors like the Laplacian of the electron density that basically quantifies the level of concentration of the electron density around the non-nuclear attractor, so how peaked is this maximum, and also the total integrated charge at the non-nuclear attractor, which is almost here 1 electron. And you see that the P4, this new P4 over MMM is overwhelmingly more electrolyte than the P63 over MCM that is stable at ambient pressure, but then that becomes an electrolyte at high pressure, and also way more stable, almost 0.1 electron volts per atom. On the non-electrolyte side, I found also this monoclinic C2 over C phase, which is almost as energetic to the P4 over MMM, just slightly less stable. But indeed, this one was not an electride. And therefore, this method can easily quantify whether a structure is a good electric candidate. But does it accelerate the discovery of electrodes? So are electrodes found more rapidly than non-electrodes? In this case, the answer seems to be yes. And on the left here, I'm showing the percentage of phases possessing a non-nuclear attractor against the generation in these crystal structure predictions. And you can see that the percentage increases, meaning that the multi-objective search tends to select those phases that are more probable to be an electride. But how? So what happens is that the non-nuclear attractor, so this characteristic of the electrode, here represented by this green dot, are always found inside metallic clusters, in this case of calcium, that are this blue sphere. And this is similar to what was observed in other electrodes, like in sodium or magnesium, and the cases that I showed before. Therefore, there is a direct structure-to-property relationship between the formation of calcium clusters in this type of compound and the appearance of non-nuclear attractors. As a consequence, the crystal structure prediction basically promotes those structures that are characterized by the calcium cluster, which then result in an acceleration of the generation and discovery of new electrodes. With this, I conclude my talk. In summary, I've shown how Podrick's reflection data can be used to assist crystal structure prediction and to improve the determination of very difficult crystal structures, and how topology and the topological analysis of the electron density can leverage and improve the prediction and the discovery of new electrodes. With this, I conclude. I just want to thank Eva, Samad, and Alberto for their help and support for these works, and also CIMAP and the University of Buffalo. And of course, all of you for your kind attention.
Thank you very much, Stefano. Very nice talk. Very important work. The talk is now open for questions, comments. Simply raise your hand, put them in the chat, or just speak up. Maybe I'll start. I'm wondering if you don't suspect you have an electride phase, when you do a structure search, is that turned on in the search in looking for new ones, or do you have to have some preconceived knowledge or suspicion that an electride will form when you look for them in your simulations?
In theory, this is not necessary. So if you activated this module and you have just the suspect that there could be an electrode, you're just curious to have them sorted. If any of them could form an electrode, you can just activate the module and it will automatically identify them. Of course, if you select a certain type of composition that you suspect that would form an electrode that could form, for example, these clusters and therefore electrodes, that of course will improve the calculation and will accelerate the discovery. But knowledge a priori is not really necessary.
And what if it's one electron versus two electron or partial numbers of electrons in the non-nuclear attractor or in the interstitial site? Does that make a difference?
It will make a difference only on the amount of the electron density that it is associated with the non-nuclear attractor. So technically, those that have a more electron density, so for example, 2 electrons per electrode, will be promoted more than those that have less electron density. And this is also translated with certain forms of the cages, because it is possible that certain shapes like, I don't know, octahedra, forms a better electride than tetrahedra because you have more atoms, so more sharing.
I see. Okay, more questions, comments? Yeah, go ahead, Christoph.
I cannot hear you, Christoph.
Christoph, you're muted.
I think that your microphone is not working. Maybe you can type the question if you want.
Well, while he's doing that, maybe I'll ask another question. Often in experiments, we have a situation where we have neither a good powder nor a good single crystal.
Mm.
So one thing that would be very helpful is to somehow use these kinds of approaches, if possible, to help with that. So when you have a lot of texture in your sample, a
Mm.
spotty diffraction pattern or incomplete rings, is there some way of building texture in and using that to as a parameter or some way of bounding the structures when you have structure present, a texture present?
So what you mean is how to use a bad quality data.
That's right.
And yeah,
How can
I mean
you
that is
help
that
experimentalists if their samples are simply not good enough for single crystal diffraction or good enough for good powder diffraction?
yeah, I mean that is complicated because for this type of methodology, it is important to try to give the code a series of peaks. So at least where you suspect that the peaks are. The fact is that you don't have to give all of them. So for example, you have something that uh, diffracts very poorly, but you can give at least maybe 3 peaks. So you have a unit cell or like just a few more. If and that technically is enough for the crystal structure prediction because even if you do not have all the other peaks to overlap with or to make the similarity index, it will consider only the peaks that you give. So we'll still try to give the best match, and that can be used to then retrieve the missing peaks or that maybe are covered by the noise or not visible by the data.
Yeah, right, right. Well, Christoph, have you been able to connect your microphone?
No, I don't think so.
Well, go ahead and use the chat if you like.
Mm.
Are there other comments or questions?
Some.
Hi, Stefano. Great talk.
Thank you.
I was just kind of, I was a little busy, so I started the talk halfway through. And, a question that I sometimes was thinking about when I see calculations and experimental data is that, is it always the case that in an energy landscape that the phase that is most stable is what's seen experimentally? And so is that an issue sometimes in calculations of what you are predicting to be the most stable is not what is actually being shown experimentally?
I mean, that's actually quite an issue because what we predict as the most stable structures is very dependent on many different factors, including the level of theory. So in DFT, for example, if you change the functional, many times you can swap the ranking of the most stable structures. Moreover, many times, what you see experimentally is maybe not the thermodynamic product, but the kinetic product that could be metastable. And with the classic crystal structure prediction of what we were doing before, so only based on the entropy, that was really hard to identify them because we were seeing very clearly what was probably the most stable one. But if you were looking at something like this other phase of calcium and lead, that is 130 millielectron volt above the convex hull, that will be completely missed. While with this type of techniques, we can finally highlight metastable phases. But indeed, experimentally, you do not always form the thermodynamic product because sometimes you form also the kinetic product. Yeah, it's in the chat.
Okay, Christophe.
You something about that. So, it up the question in the chat. So, how much your results depend on the solution of data? Fortunately, we can use better data. So, in the case of a sodium HP4 in a RAM compression, I was able to use from 3 to 5 peaks only. The quality of the data was very bad and the diffraction was very poor, but that was enough to identify the phase that we think was formed. So this distorted sodium HP4. I think that really the bare minimum would be at least 3 peaks because if you wanted to, deform and optimize a unit cell that is not just cubic but orthorhombic and below you need at least 3 peaks. But that's probably sometimes enough because if you combine that with the FT calculation that tells you which are the most stable, you're already in a very good position to have quite a good ranking of the structure. So good data quality, as it's seen in the case of Vaterite, can be very, very important because those are more complicated systems. But for more simple system, maybe one element or two, we can use also better quality data.
Okay, good. Thanks. Okay, any more comments or questions?
Yeah. Barbara.
Barbara.
Hi, nice
Hi.
talk. Quick question, I might have missed that part. If you have motives or some information that you have good guesses about coordination numbers or sums of parts, can you input in, and would that help a lot?
Can you repeat the question? Sorry.
Can you input some information? Say, I believe my coordination
Additional
number.
information. Okay.
Mhm.
Yes, this thing that some other developed, this multi-objective search, has basically no limitation on the number of objectives. So, for example, if you wanted to combine the product diffraction with, I don't know, the volume of the unit cell that you suspect is that, or also the coordination number, you technically can do that, you can do it. So the more information, the better, and that helps a lot the crystal structure prediction, especially if your system exists in a very wide potential energy surface landscape. What I mean, if it's if the dimension, so it has more than 3, 4, or 5 elements, the dimension of your potential energy surface is really big. So the more information to be selective in this search, the better. But that's how I think that experiment and theory can really help each other to find a good solution in this case.
And what if you have multiple phases in your pattern?
Yeah, that's initial was a real problem, and it is a problem. But the way that the code works is that if structure is optimized and the particle refraction is calculated for that structure, then it will try to find the best solution in terms of similarity index with what it has. That means that it doesn't have to fit with everything, but it just has to find the best fit. And that's very important and very useful because maybe we find a phase that fits very well with only a few peaks. So we know that that phase, those peaks are generated by one phase. And then maybe we can remove those peaks and then repeat the iteration with only the peaks that we were not able to index. And we found that maybe another phase that maybe was formed 10% compared to the total system is actually producing or contributing to the other part. So even if the sample has more than one phase, this is not completely a problem, so we are able to separate them or to recognize them.
Thank you.
Okay. As you said, at the beginning of the lecture, you are looking for the global minimum on the path. That is a problem in itself. Start running. So yeah, to answer to the second question by Christoph. So all these methods are trying to find the minimum, the global minimum, but of course it is impossible to know if you have found the global minimum unless you have mapped every single minimum of your potential energy surface. That is good. This is actually an NP problem, and is basically almost impossible to solve, but that's why we try to perform a very extensive crystal structure prediction and be sure or try to map as many minima as possible. But in theory, you cannot be sure unless you map every single minimum.
And when these genetic algorithms were being produced, they were often cross-checked against one another because of this very problem. The ones
Exactly.
By different groups all around 2005. And the encouraging news was they were all converging, but there was a lot of cross-checking of different approaches to address that very problem.
And that happens for a very specific fact, which is that the lowest minimum, so the one that has the lowest energy, to that minimum is also associated the largest basin in the potential energy surface. So you know that the most stable structure will also take the largest amount of space in that multidimensional space, which basically is helping crystal structure prediction to find it. So the lowest minimum wants to be found in a way, so it's easier to find.
Yeah. Shafiq has a question.
Yes, very interesting talk. So I'm wondering if the prediction depends on the form of multi-objective function you have. Like I saw you had a linear combination of entropic effect and enthalpic effect. So if I change the functional form, would the prediction be different, or you still pretty much get the same result independent of the form of the multi-objective function?
So something that we tested was also the Pareto front. If you're if you know that the type of technique which is not a linear combination of just parameters, but works in a very different way, and we basically found exactly the same results. So in that case, switching from a linear combination to a type of Pareto front, we still are not seeing any difference, at least for the cases that we studied. I think that the form of the linear combination is very handy because you can easily, twitch it and decide how much importance to give to the similarity index. But it's surely not the only possibility. One could imagine for other functions that may be changed during the crystal structure prediction that may evolve. So at the beginning, focusing a lot on the entropy and then more on the similarity index and with different factors. But this is a possibility.
Okay, thank you.
Thanks very much. Okay, that's bringing us to the top of the hour. Thank you again, Stefano, for a very nice talk. Very interesting.
Thank you.
Very important work. So thank you all for joining us. See you next time.
Bye.